photosynthesis, photosynthesis.
How's everybody doing tonight? Good, how are you?
I'm doing fine. Okay, I have 6 o'clock. I guess we'll get started. Give me a green circle if you can hear me okay. Okay. Samir, you got one? Okay. All right, so let's go ahead and get started with, first of all, just a very quick review of the homework you had for tonight. And what I did is I reworked the problem myself, but I have to apologize because I copied it from a piece of paper onto this. And so I may have some X's or things in the wrong places, but it's more from my point of view is going to be how I did it, not whether all my X's and zeros and everything are in the right spot. So we have a truth table over here on the left, which we were asked to use the Quinn-McCluskey method or algorithm to come up with a minimum sum of products. Give me a green circle if you did this and you think you got it 100% right. Should be most of you. Yeah, that's about the percentage I would have expected. Okay, so I just copied the truth table out of the slides. And then I grouped them by number of ones that are turned on. So this has 0 ones. These two terms had 1 1. These had 2 ones, 3 ones, and 4 ones. And what I put in this column are only the rows that have a fundamental product of 1 or had a don't care. We had one case where we had a don't care. Now, obviously, they're not right directly across from each other because the editor doesn't let me do that, but you get the general idea. Then what the algorithm says to do is to go to my lowest number and compare it against every other value in the next group. If it matches anything, I need to mark it. I don't have a check mark, so I just put a little dot in front of it. So this guy matched one of these two, maybe both of these two. And when something matches, we mark being used up because we have a better term. So this matches this in that way. This matches this in that way. Now, once I've done all those matchings, I have a group, so I can close off this group over here as well. Now I need to come back, starting with this guy. Even though he's marked off, I have to reuse him. And I need to compare him against everybody that's in the next group. And so we get matching this guy 0x01, so he gets put here. Both of those get marked off, but we're still using him. He doesn't match anybody else. Now this guy matches the second guy. So they all get tick marks, and those two other guys get put into this list. Since we finished with this group, we can draw a line. Now we're going to repeat that. This guy against these guys, creating a group. And then this guy, these guys against this guy, creating a group. In this, by the time we had finished doing that, every one of these items has a little dot next to it and has been checked off. It matched something, either from above or from below. So I'm going to move to the next column and do the same thing. Compare this guy against everybody in the next group, marking them off if they match and writing them over here if they match. Got done with this column, and I noticed that this guy and this guy did not have dots next to them because they didn't match. They didn't match. So I marked them with a $sign to indicate that they didn't match, meaning they're going to be prime implicants. Now the last column, I need to get rid of duplicates, so that's a duplicate. I just don't use it. These two are duplicates, don't use them. And then I take what's in this group, which is only this guy, and see if he'll match against this guy. He won't. So that becomes a prime implicant. This guy against these guys. And find out ultimately that this, and this are my prime implicants. So I have 6 prime implicants. 4 of them have 2 terms. 2 of them have 3 terms. Now, before we go to the table of choice, let's put a Carnell map up here. 1 1 0 0. 1 1 0 0. 1 1 x 1. 1 1 x 1. 0 0 1 0. 0 0 1 0. And finally 0 1 1 1. 0 1 1 1. Okay, now what we're headed for in the other table over here is to figure out which of these groups are the largest and which ones cause us to be able to cover the most territory. One of the things we can notice is we know ultimately that's going to be a group. We know that ultimately this guy is going to be a group. We know that this guy has to get picked up somehow, and there's nothing 4 around him, but there is a 2. So we know that's going to pick him up. Now, I have to be careful here, because if we assign this a value of 1, we're going to take another group. We don't want the extra group. So hopefully, in our algorithm, we want to make sure this gets picked as a 0 so it doesn't get covered. So ultimately, we know from looking at the Karnow map, this is going to be the equation. We're going to have one thing that has 2 terms, a second thing that has 2 terms, and one thing that has 3 terms. Anybody have any questions about the steps we've done so far? And again, I apologize if I copied something wrong from my other page. Just bear with it. Okay, so we build the table of choice. I had a little Karnow map thing sitting down here just so because I didn't have this handy. What I'm going to do is I'm going to mark, first of all, with X's. All these big Q's were originally little X's. Everything this covers. So this is going to cover the 4 cases where both X's are zeros, the X's are 0, 1, 1, 0, or 1, 1, which these first 4 cases. So put little X's here. The second guy is going to cover 4 things, but we only have 3 of them marked. That's actually this row right here. Notice that ultimately we're not going to pick any of those, but had this guy been a 1, it's one of the optional things we could have picked as a set of 4, either that or this. But we don't need either one because this was a don't care, and if it's a 0, we get less terms. Now we do the or x1, x1, we get 4 terms. That turns out to be the middle set of 4. The next guy, x1, 1x, covers 3 terms, which would have been 4 if this guy had been in a 1, which is really this set of 4 terms here. So we don't want to pick him ultimately. We have this guy here who has coverage on these 2 guys, which happen to be the 2 that are in the column here. And then finally, we had coverage for these, which are 0, 1, 1, 1, and 1, 1, 1, 1. So 0, 1, 1, 1 is here, and 1, 1, 1, 1 is here. They would be if we were going to pick this set of 2, which we're not going to pick because the bigger group completely consumes that. So after we've done that, we come back and first of all, we find all the essential primes. The essential primes are the ones that are the only term that covers something. So this guy is essential because he's the only guy that covers these 2 things here. So he's additionally going to bring up these 2 because when he covers those 2, all 4 get covered. This guy is an essential prime because notice he covers this guy exclusively. So he's going to be covering all of them. So the only 2 we don't have covered are this guy and this guy. As we look down the rows, we happen to have a guy that covers him. So I changed all the X's to Q's for the ones that we're actually needing. So the 3 terms we need are this guy, and that guy. So 2 terms, 2 terms, and 3 terms. And we pull out the equations for those. We're going to see it's not A, not C. That's the first guy. The third guy down here is going to be a B and a D. And the guy second to the bottom has an A turned on, has a C turned on, and a not D. So this is the equation, assuming I didn't copy anything wrong, that we would have gotten following that procedure. Anybody have any questions about that? Okay, I'm not going to collect those tonight because I already have a pretty good idea who did what. And these will be on a test. So you don't want to say, oh, yeah, we did that once, I'm going to forget about it. So occasionally when we're doing a problem, you might, when you're doing the Karnow mapping, you might say, well, let me just try Quinn McCluskey also. And as long as you're doing it for small amounts of inputs, they happen rather quickly. Obviously, if you have a table that's got 7 or 8 inputs, this part takes a long time. But as long as you're careful and move item by item, it's very, very doable. This one's also a lot easier to program as a computer program compared to Karnow mapping. And I've seen lots of implementations of this. Ed, if nobody has any questions. Scott, do you have a question?
Yeah, I ended up with the same final answer that you did, but some of the interim steps were a little different. Is there only one correct way to arrive at the interim steps?
Well, you might actually pick different boxes, but otherwise, and the ordering of how I list these in the table might be different. But this is fairly algorithmic. It doesn't really give you a lot of options.
The process
of what
that converts solar energy
only real
into chemical
choices you get are
energy
down here, where
directly
you're
or
picking
indirectly
and
nourishes
possibly
the
picking one
entire
of the
living
other
world.
rows. But then eventually you'll wind up with the correct answer anyway, because you'll wind up with the one that minimally covers everything. So I'd have to take a look at yours to see if you did anything that was different than I did. Maybe you just did them in a different order.
Now, like the X111, for example, I ended up with that not being a prime implicant. So I'll need to take a look at what I did and see if
see what happened here. Well, one thing that I almost slipped up on was I thought for a while this was a duplicate until I looked at it carefully. Right, this had all duplicates, and most of the problems we worked by the time we get to the last table, it's something and its duplicate, something and its duplicate. So I looked at this one and without thinking just said, oh yeah, that's a duplicate. Well, it's not. It's actually a real term. So you could have done something else like that. Okay, let us move ahead. Let me see, what is this?
Professor, I agree with him.
Okay.
I canceled out X111 because it matches up with X101, which you don't have in your list. But if you look from the 2 digits, you have 0101.
Mm-hmm.
And then from the 3 digits, you have 1101.
Yeah, like I said, I copied this from a piece of paper. I may have omitted something over here.
Okay, so
in which case the term will go away anyway.
Okay.
Yeah. Okay, let us move ahead. Do I need this for the moment? I don't. And we actually might need that again. We'll see. Okay, what I want to talk about next, let me double check my list here. I want to talk about the concept of some digital components. We've been kind of just arbitrarily writing down truth tables and really with no purpose in mind. I think we probably with a couple said, oh yeah, this will get you the maximum number of ones in a table. And this other table over here kind of shows us that it has a guard or a gate on it. I might have called it either of those or even a gateway or something. But there are some fairly beginning formal types of things we can look at, which I think might be useful for us to do. And some of these I'll give you copies of, some of them I won't, but let me bring an example over here of something we're going to call a digital component. I think the first one on my list is probably I. Okay, now, this is a gate that we're going to learn about to give us an idea of a function we might include in a design if we needed to cause some particular behavior to occur. Notice we're talking at a little bit higher level than just simply A's and B's, and Y's. Although this is going to be a function of A's and B's and Y's, we're going to say what we want to do is do the particular function here, which is using an AND gate to block or transmit data. And this is the problem type of thing you would find in a particular example. You wouldn't necessarily be given a truth table. You'd want to have some purpose for why are you doing the truth table. We will have truth tables, obviously, because that's the way digital logic is expressed. But let me talk about what this picture is indicating to us. So if you see one in the wild, you'll have a little bit of an idea of what we're trying to do. First of all, we don't know yet what a register is. A register, though, is simply going to be something that can hold data, in this case, 6 bits. We've named them A, B, C, D, E, and F, across time. So somehow we'll load this with some data, and then it will continue holding the data at each of these pins, let's think, on a digital device. And our goal is to put the value of A or B or C, any of the values of these items, on the output, our control, meaning only when we want it there. To do that, we're going to declare a signal called enable, and we're going to tie it to one side of each of the AND gates. Notice these are AND gates. And upon asserting the signal, meaning making the enable a 1, then what we're trying to do is have A pass through to Y. So basically we're using the enable signal as a gate. So let's talk about that for a second. If we have, actually, that's probably not even the right tool for that. What we have is this guy. In the truth table, for an AND, where we have A, B, and Y, we only have 4 combinations of things that can occur. And our equation that we're using here is Y is equal to A and B. Now, don't confuse the A over here with the A over here. I mean, these are just the names of signals. This is the name of the first 2 signals in any of the AND gates. So in the third gate, even though the name coming out of the register is E, its name going into the AND gate is A. So this is the truth table. The important part about our truth table for this is that the only time we're sensitive to the inputs is on the case where both of the values are a 1. And that's exactly the condition we need to pass a 1 through in our digital component over here. So what we're doing is, if you think of A as being a blocking device, it happens to be the second input here, but that's okay. Anytime we make one of the signals a 0, the output is forced to be a 0. So if we make AB our gate, anytime it's a 0, the output's a 0. But if it's a 1, the value of B gets to pass through. So we can basically block any signal by passing it through an AND gate and then making the opposite pin or the other pin be either low, which is a 0 when we don't want to pass the data, or a 1 and high when we do want to pass the data. So that's a fairly straightforward thing, but we're going to see this a lot. And very often, when we're using these components like this, the description of the problem is going to be something about passing data through. And we want to remember that one of the ways we can do that is use an AND gate to block the AND from passing any data, because it'll always maintain the 0 value. Anybody have any question about that particular gate? Okay, the next one we want to look at is called a controlled inverter. Now, the idea here is that I have eight outputs from a register. I'm going to pass them to Y, but sometimes when they go to Y, I want it to be their inversion. Think of this as the first step of a 2's complement. Invert all the bits, right? Well, here's all the bits at A. If I invert them, Y should be the opposite of whatever they were. We can call this a controlled inverter. Again, that might be the term you hear in a design. You might not hear, oh yeah, I use a XOR gate to make it happen. You might instead hear or realize that what you really need is the inverse of the problem, or of the bits you have. And again, we're going to use a signal just like we did in the blocking thing to handle when we do the inversion. Or let's just add our truth table down here. Y is equal to A XOR B. Let me put lowercase. So let's assume that the first signal here is the invert signal. Notice that B passes directly through to Y if invert is low. If invert is high, however, we get the opposite of B on the output, which is exactly what we wanted to do. Under the control of A, invert B. And again, this is one of the problems somebody might give you, and you have to realize, oh, yes, I need to invert all the bits. How do I do that? Well, a way to do that is using a controlled inverter. Anybody have any question about those first two examples of digital components? Okay, everybody give me a red light circle. Okay, thank you. I have the automatic attendance thing turned on tonight, and periodically I want to check that it's doing the right thing. It's been really good about ferreting out people that have been turning on their computer and then leaving. Remember, if you accommodation for recording, that's while you're in the room, not record something and go somewhere else. So be very careful about how you use your accommodations. Okay, so there's two things which are very useful to us. Let's find a third. Here's one that's going to allow us to generate odd parity. We've seen odd parity with our ASCII characters when we want to transmit them. We can imagine that the 7 bits are sitting here, and we need to produce a 8th bit, which is a parity bit. And the parity we've chosen is odd. So what we're going to do is we're going to use this very elaborate looking exclusive OR here. It's a 7. And we're going to then invert the signal. If we didn't invert it, we would have even parity. We want odd parity. So one of the uses of this, now, admittedly, that XOR gate is a little bit fancy to look at and to try to get a grasp on what the heck it might be doing. So let's just take a simple case just so I can illustrate to you. I'm not going to do all 7 inputs, but you can extrapolate to it must work the same way beyond the 3 inputs we'll use. Let's assume for a second that we have a 4-input XOR gate. A and B and C and D. I'm going to separate them like that. And I actually copy this and paste it below. I should be able to take and change those. So this is just a simple truth table. Let's assume for a second that I were taking 2 of these into the equivalent of a single XOR gate, this table up here. Well, the output, let's call this output W. The place where I get the ones is anywhere things are different. So the first 3 lines would be, well, if I ever get that typed. Because these are all zeros. These guys, X4, are all going to be 1s. And again, these are different, so they'll be 1s. And then finally, the last guys down here will be all zeros. Oops. And then let's say we have an X variable. Same thing's going to happen here. Let me actually put some spaces in here so I don't have to type as much. They're different, or I'm sorry, they're the same, so we're going to get a 0. They're different, we're going to get a 1. Different, a 1, the same, we're going to get a 0. Okay, they're the same. They're different, different, same. And we got the same thing. 0. 1, 1, 0. Somebody check my work for me here because I can barely see the screen from where I'm sitting. And we'll go ahead and put another space out here so we can type some more. We'll call the next column Y, our output. So what we did is we took 2 of the inputs and XORed them together to get this. 2 more of the inputs, XORed them together to get that. Now let's take these 2 and XOR them together, and that'll be the same as a 4-input XOR gate. And let's see what we get. If they're the same, we're getting a 0. If they're different, we're going to get a 1. Again, check my work for me. Ooh. Okay, now let's assume for a second that everywhere y is, it's an odd number. If y is turned on, let's go over here and count the number of ones we have. We have none, so it's not odd. We have 1, so it is an odd number. We have 1, it's an odd number. 2 we don't. 1 we do. 2 we don't. 2 we don't. 3 we do. 1 we do. 2 we don't. 2 we don't. 3 we do. 2 we don't. 3 we do. 3 we do. 4 we don't. So by using this as though it were just a 4-bit, where we only had 4 A's coming in, passing it through an exclusive OR, and then taking the combinations of each pair and passing them through a 2-input exclusive OR, we've generated the fact that, yes, in fact, what you're going to get is something which you could use to generate odd parity. Now, in our case here, because we use 7 instead of 6, we need to invert it one more time to actually get the odd parity. Now, this is good because if I ask you, to take and build something which could transmit an ASCII character, one of the steps would be to generate parity. It's easy to generate mark and space parity because you either just add a 1 or add a 0 to the end of it. Even in odd, that's easy to do now. All we need is to have XOR gates and an inverter. If we wanted to have no parity, well, it doesn't really matter what we hook it to. So we have another tool in our tool set. And we also can take a more complicated circuit like this and derive what it must be doing. And again, I didn't want to do 7 inputs. It just takes too long. Robert?
So I'm assuming the reason with 7 it's inverted and with 4 it just naturally comes out with the correct answer is because for even it'll come out even numbers, and for odds it'll come out odd.
Yeah. And it has to do with we have less pairs of XOR gates to work with the odd. We have kind of one floating input that we have to deal with a separate XOR gate. Okay, let's move ahead here. Taking what we learned from that, we might encounter something looking like this. We have 2 registers, and each of their corresponding bits, A5, B5, A4, B4, all the way down to A0, B0, are passing through a XNOR gate. It's not a XOR, it's a XNOR. Okay, so instead of this function, the XNOR, put an N in here, is the opposite. 1, 0, 0, 1. In this case, if they're equal, we get a true, which is exactly what we'd want to do. If all of the pairs are equal, meaning if all these generate 1s, and we AND all of those 1s together, this is just a big jumbo, 6-input AND gate, we'll get a bit out which we can say means equal. So anytime the 2 registers are equal, that flag down here will be turned on. And notice that these are XNORs. They're an XOR gate with an inverter on the tip end of them. So they invert the XOR function. And again, this is a block. You need to select between different data that you're going to have only when it is equivalent. You know, if A and B are equal, we don't have to test B because we know it's the same thing that's in A. But this is a good way to generate an equal flag. We can imagine in our CPU that we build at some point that when register A and register B happen to contain the same thing, we can turn on an equal flag that a branch instruction could test and say, if equal, do something that's different than if it's not equal. Anybody have any questions about this one? Okay, one more component before we still have some other things we have to learn before we can look at some of the more advanced components, but this one will be fun. Let's see if I can get it shrinky dinked down here. I don't think it's going to fit on the screen, but what the heck. Oops, I've lost it. Oops, that's not it. Is that it? No. Oh, you know where it is? It's over here. It's probably good enough if you can see the detail. I'll zoom in a second. This is what's called a 1 of 10 decoder. We're going to basically pass in a binary number in the register that's up here. Remember our bus? We have the positive value, and then we have an inverter, so we have the not value. So this is A and not A, B, not B, C, not C, D, not D. So a signal will appear on A, B, C, and D. Now, if it's a 0, that means the inverted signal will be a 1. If it's a 1, that means the main signal will be a 1. These two will always be opposites. Those two will always be opposites. So what we did is we put 8, is this 1 of 10? Let's see, 1, 2, 3, 4, 5, yeah, 10 AND gates, and there are 4 input AND gates hooked up uniquely. The first is hooked to all the inverters. So think of that as being 0, 0, 0, 0 when A through D is a 1. But if A to D is zeros, then the inverters will all be 1s, meaning this AND gate will turn on. If it turns on, the output is a 1. The second one is hooked to 0, 0, 0, 1. 0, 0, 1, 0. 0, 1, 0, 0. So they're going to be hooked to whatever is unique to them, each one. This is hooked. Let me blow this back up again, because we don't need to see them all. This guy is responsive when the binary number is 0, 0, 0, 0. 0, 0, 1. 0, 0, 1, 0. The 2 is in here. 3, 4. All the way down to 9. Now, what's going to happen if the register contains hex A through F? Raise your hand if you know. Do all of them turn on? Does the wrong one turn on? Somebody take a stab at it. Stephen?
Do only 6 of them turn on?
Okay, that's one possibility. Robert, what do you think?
I was actually going to say something similar, but I
Okay.
thought about it and I'm probably wrong.
Okay. Anybody else have any other ideas? The thing to ask yourself is, for example, bit pattern. What bit pattern would an A be? It would be 1, 0, 1, 0. Meaning when I go up to these gates up here, I have to find one hooked to the positive, the negative, the positive, and the negative in order for it to be turned on. However, if I go through all of these, they're hooked up to the numbers 0 to 9. None of those match this number. Therefore, if A through F is in the register, none of these turn on. Because effectively, at least one of the lines into all of the AND gates will be a 0. Remember, we said that blocks the signals. If we had another gate and we wired it up so that it was hooked to A, not B, C, not D, when A was turned into the register, that particular one would turn on. Does everybody understand that? This is an important circuit. Robert?
Now, would that cause an overflow error?
Nope.
Okay.
It just simply wouldn't turn anything on. Now, if the guy looking at these signals cared, he unfortunately is going to see no ones turned on, right? This is going to turn on 1 of 10 signals. So if none of the 10 signals are turned on, the guy who's listening to those 10 signals had better have a plan. What does he do if nothing is turned on? Well, you could think about it this way also. What if this contained the number of the door that's open into the building and there's 10 doors and no doors are open? Well, none of these should be turned on. However, if you think about it, there's no way for us to turn 2 of the outputs on because any combination here is going to uniquely identify one of these signals. So this would not be a good circuit to use if you had to have multiple things turned on. It's beautiful if you only need one of them turned on. We do have the restriction that those register is going to have a special case if it contains a number that it's not encoded to do. But we'll see when that's useful and when that's not. And we'll clearly have it's not clear to you, but it's clear to me we're going to have a very big use for this in part of our CPU where we're trying to recognize which instruction is being presented on the bus. But you don't know that yet? That's a couple weeks off. Okay, I think we've covered all the digital components that I want to cover for the moment. Does anybody have any questions about any of them? The AND blocking circuit, the controlled inverter, the odd parity generator, the word comparator, or the 1 to 10 decoder? If you go to the website and go / digital with a capital D, components with a capital C, .zip, and make sure that's the right name. Where do I have this notepad handy? You go to that spot, you'll download those files I just showed you. You should do that. Give me a green circle when you have it downloaded. Okay, we need to move ahead. We've talked about addition as a, the maths, if you're from England. And we said that if we're working in, let's just work in decimal for a second. We wanted to add those numbers up. We simply start at the right-hand side, working our way to the left, where the first column on the right-hand side adds up two numbers. So it's going to add an 8. Now, if 8 had exceeded 10, we would have to have a carry into the second position. I'm just going to write a little C there for carry. In our case, it's a 0. But the second column and the third column and the fourth column and the fifth column all have to contend with an extra number being added in. We have names for these particular columns. The rightmost column is formally called a half adder. It takes A and B in as inputs, and it produces a carry and a sum. So we'll write down our numbers here. I'm adding A and B together, and they're zeros. The carry will be a 0, and the sum will be a 0. If I add A and B together and one of them is a 1, carry is a 0, sum is a 1. And finally, if I add up the two numbers and they equal 2, carry is a 1, sum is a 0. Now, logically speaking, those could be considered to be two truth tables. The one on the left, if we look at the function, seems to have a 1 only when A and B are both 1s. So we could say carry. We often call this one carry out. Now I'm hungry. Carry out is equal to A and B added together. The sum is equal to, well, which function is this? We've seen this before. Raise your hand if you know what that function is. Yeah, it's an A exclusive or a B. So for a half adder, we could build these and this circuitry fairly straightforwardly. That's not going to be a big deal for us to do. Let's work through the other columns. The other columns are called full adders. It's going to have an A, a B, a carry in. It's going to produce a carry out and a sum. Let me change this to say C out so that it matches everything else we're doing. So there's three inputs, so that we know this is going to have 8 lines in the table. Okay, so if A and B are 0 and there's no carry, we're going to have a sum of 0 and a carry of 0, or carry out of 0. Now, if we're adding two zeros together, but there's a carry out is still 0, but the sum becomes a 1. The same thing would be true for two other cases. The case where B is a 1 and everything else is a 0, in the case where A is a 1 and everything else is a 0. Now, if we add A and B together, B is a 1 and carry is a 1, we get the number 2, which means it can't go in a single column. That means carry has to be a 1 and sum has to be a 0. And all the ones that take 2 in will look like that. Finally, the last one actually adds up to 3, which means we not only have a sum, but we have a carry. If you think about this as a 2-digit binary number in either case, this is 0, 1, 1, 2, 1, 2, 2, 3. Up here we had 0, 1, 1, 2. We made the output just a number. So what we want to do is we want to look at this and see if we can figure out what the truth table is for each of these. Well, for carry out, 0, 0, 0, 1 looks like an and 0, 1, 1, 1 looks like an or. So let's put that in a Carnot map and see if we can reduce that down to something. What is this? This is 8 inputs. I think I got one here somewhere. Okay. So we're going to put 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We know that those guys combine, and those guys combine. We'll lose a term because we've put things together, which is great. So this is the not A row. This is A. This is not B. Not carry in. I'll just write C. Not B. Carry in. BC. And B. Not carry in. So Y is equal to this group right here, which is AC, or, oops, this group right here, which is BC, or this group right here, AB. So the carry out, so this is really Y sub carry out, is a function of A carry in, or B carry in, or just AB. This column right here is going to be problematic. 0, 1, 1, 0. 1, 0, 0, 1. Anybody see what combines there? Raise your hand if you can see how to reduce that. What do you think, Dante?
Isn't there's no way to reduce that because we can't group by angles.
That's right. You're exactly correct. And I'm assuming that everybody who had their hand up knew that as well. Very good. Okay, so whatever we have there in the way of an expression of a statement is going to have to be what we're left with. And it may be easier than we think, because if you look at the first part, it's a ZOR, and the second part's a ZNOR. So there might be something tricky we can do if we use ZOR gates and ZNOR gates to make it happen. So let's look at I want to make sure I'm getting the right one here. A circuit for a half adder. Again, this is really a digital component. That's exactly what we reduced it to. A ANDed with B gives us the carry. And A XORed with B gives us the sum. Now, if we were building this out of 2-input NAND gates, we'd of course have to turn this into NAND gates, but it takes 5 gates to do, but we could make it happen with our sum of products logic. So this is a circuit we would use if we needed to have a half adder, the right column or single column of addition. We saw also, though, for the next column and those that follow, because we may have a carry in, we might need to have a full adder. Full adder can actually this way. One of the things that is a little tricky is the fact that we remember we had A and B, A and C, B and C were our ANDed things to get the carry. And the sum, we said, looking at the table, the top part looks like a XOR. The bottom part looks like a XNOR. Remember the discussion I had with somebody about even and odd a while ago on XORs? Do you notice that this guy, this row, has an odd number of ones? This row has an odd number of ones. This row has an odd number of ones. That row has an odd number of ones. So this is exactly the truth table for a 3-input XOR gate. Since we don't normally use, we didn't learn this, but now we know it. We can always come look this up again if somebody were to ask us that question sometime. So a 3-input XOR gate is exactly what that describes. Yes, it's not reducible in a sum of products way. You've got some horrible sum of products going on there. But it does do exactly what we need it to do. So we would have to build one of these for each column, and its carry goes to the carry in, which is the C, of the next stage to its left. Now, when we would hook one of these up, conceptually, this is what we have. And this is what we were just describing. We have, if this is a 4-bit adder, we have a half adder on the right and 3 full adders. The first one produces a sum and a carry, which goes immediately to the next stage. Each of them produce a sum. Each produce a carry that goes to the next stage, except for the last one. This guy drops on the floor if we're doing addition. It's an overflow when we're doing 2's complement. And then we have as inputs the 2 A and B's. So this guy has 2 inputs, A and B. This guy has 3, A, B, C, A, B, C, A, B, C. Everybody see how that works? Now, we just drew a square box here to indicate that for full adders, this is what's inside there. For half adders, that other picture I showed you would be inside there. Together something in a simpler term. It's like a section heading where you haven't expanded the section to see what's inside it. If you tell me full adder, I picture this in my head. Anybody have any questions about that construction there? Okay, now if we were actually going to be building this inside of a microprocessor, there is one enhancement we could make to it, which would make it more useful to us. And that would be basically, let's turn this right guy into a full adder, which means he's going to have a carry coming in. With the carry, well, the carry could either be a 0 or a 1. For simple addition, I want it to be a 0. But if I had some way of inverting B, if I could take B and change all its bits from what they are to something else, and I pushed a 1 in the carry bit, wouldn't that be doing the 2's complement? Invert all the bits, add 1. So I could turn this into an adder subtractor rather easily. I could do something like this. I have 4 full adders, each of which produce a sum. The last one's not used. It falls out. If I overflow unintentionally, I get a wrong answer. If I overflow because of negative numbers, that's fine. The one on the right becomes a full adder. And I'm going to take this signal I'm going to call sub or subtract. When it's a 1, I'll be putting another 1 into whatever I'm adding here. If it's a 0, meaning I'm doing an addition problem, the full adder will just be adding A and B together. Notice how I'm also using the subtract signal as a controlled inverter. I'm using it to invert B anytime I want to do a subtraction. 2's complement says invert all the bits, add 1. So this little box here will add up 4-bit numbers or subtract 4-bit numbers. Take a look at that and appreciate the compliment that the components are giving us here by being able to do that. Subtract serves 2 purposes. It operates as a controlled inverter signal, the thing that says do your inversion now, and it also acts as input to the first stage on the right's carry, so we can add an extra 1 to those inverted bits when we're doing a subtraction. And adding a positive number with a negative number, where we've inverted, 2 positive number, then we're going to be able to make it happen. So if this had contained the number 5 across here and the A, and B contained the number 4, if subtract is a 0, we would add up 5 and 4, and the sum down here would be a 9. If we left the numbers alone and we changed to a 1, well, we're no longer getting a 4. We're getting a negative 4. So when we add the negative 4 to the 5, we get a 1, which is a subtraction. We get 5 minus 4. Over here, we got 5 plus 4. Give me a smiley face if you kind of get that. You know where they're hidden away. Mikkel, did you get that? There we go. Okay, anybody have about addition and subtraction? I think we can go to the website. I think I put this one out there also for you. Let's see. I did. Notepad. So what you want to do is get arithmetic.zip on the web page. Capital A in the word arithmetic. And give me a green circle once you get that. Okay, good. That looks like most of you got it. Let me kind of clean my screen up here. We're going into a different set of things right now. Don't save. Keep that. And I opened a lot of windows, didn't I? Wonder where that window is. Must be on my other, yeah, it's on my other screen. Okay, we're going to talk a little bit about some hardware. And I briefly mentioned it the other night, but didn't give you much detail about it. We're going to talk in a little depth. But it's stuff you should know. Let's see if I can make this a little bigger. I don't know why everything's so skinny over there tonight. We're specifically going to be talking about something called transistor logic, abbreviated TTL, transistor logic. These are circuit chips, which are of the size of what we call integrated circuits, or ICs. Specifically, the transistors we're using inside of these are of the bipolar type, which is what we've been talking about designing around. There are other families. One of the other families is called CMOS. Complementary, that might be an I in there. I think probably is. Complementary metal oxide semiconductor. And its type of transistors that it uses are called, well, they're a form of FETs, which are field effect transistors. But specifically, they're mostly MOSFETs today, which are metal oxide semiconductor. Field effect transistors. The difference between the two is technical, but very simply, bipolar transistors amplify current. And these have the effect of amplifying voltage. We're going to be talking about this family. In particular, we're going to talk about, let me actually write below this. We're going to talk about a family called the 7400 series. Now, these chips have been around since the 1970s, but they are one reason that we can have computers today. Even just having a transistor would probably make the things not of a size that we could deal with them. The 7400 series was kind of the door opener. And when it was invented and first used, it brought a different way of the types of things we could design with electronics. Now, there's some naming conventions that we need to get a little familiar with. One of the naming conventions is very often they'll start with a 2-letter prefix or 3-letter prefix, which is the company that makes this particular chip. Anybody want to take a shot at the name of the company that makes the SN chips? Excuse me. Dante?
This feels like a complete Hail Mary, but I'm gonna go with IBM.
IBM? They do not, but that's a good guess. Turns out that this is one of the cases where the chip is old enough that the meaning of the thing, while it has stuck to it, does not describe the company that makes this. This particular chip that start with the SN are made by Texas Instruments. And they happen to use SN as their company abbreviation. It actually stands for silicon something, I believe, or semiconductor something. It was a very old name that was attached to it. Now, additionally to this, sometimes we will find on the right-hand side of it something like a P or a PD. This is where packaging information goes. This is in something called a plastic dip. DIP, dual inline pins, meaning it has 2 columns of pins, P, plastic, made out of plastic, casing. We'll forget about that for the moment. Also forget about the SN, it's not critical. But, what's going on there? Why is that erasing the wrong direction? The numbers we have left have 2 parts to them. There's really 3 parts here. There's 74, which means it's commercial TTL. There's also 54. We could have a 5400 chip, which is military. So the tolerances and things on that chip are better for military type operations than with the 74, where the 7400 series is better for commercial activities, or a vacuum cleaner or a toaster, not a weapon. The other thing is that the number that's here basically tell us what type of integrated circuit it is in the TTL family. And depending on what the number is, for example, 7400 is a NAND gate. It's specifically a quad 2-input NAND gate or NAND chip. Quad means there are 4 NAND gates inside the chip. Each of them have 2 inputs. .7402. 7402 is a NOR chip. Specifically, it's a quad 2-input NOR gate. Set of NOR gates. There's 4 of them in there. 7404 is basically your NOT gate, called a hex inverter. Perfect, just in time for Halloween, right? The hex part. Now, the hex just means there's 6 inverters inside the chip. And there's all sorts of numbers that mean different things. Now, additionally, over the years, the part has changed the way it's manufactured and been changed to do different things. For example, the standard family looks like that. One that uses low power might look like that, where the L in between says it's a low power technology chip, and the specifications for it will be different. The 74H00 is a high speed chip. 74LS00 is low power using Schottky diodes. Now, kind of understand that. Imagine that you were moving a lever back and forth that's hinged in something like a joystick handle. And assume that when you move it all the way back toward you, it latches in a little notch that's there. And to move it forward again, you kind of have to push it to get it out of the notch, then move it all the way to the other end where it locks in another latch. That's kind of the way a regular circuit changes its signal. A Schottky diode is put in the circuit to prevent it from latching. So basically you can move it back and forth faster because you don't incur the time it takes to latch or unlatch itself. And it can be made to perform just as well. But it can also be done so that it uses a lot less power. So we'll just talk about this set right here, but there are many others. And of course, there's different families inside the military grade as well. There are a bunch of specifications that we should know about the standard family, because all of these exist. They maybe have different values, but that's not important. We have to know what to be looking for. One of the things, for example, to look for is for the chip, what's the VCC safely? Well, it can go from 4.75 volts up to 5.75 volts, where 5 volts is what most people would try to operate it around. Now, there's a bunch of voltages as well we need to talk about. One of them is, what is the voltage on an output when it's producing a high signal? Well, it's 2.4 volts as a minimum. Typically, it's about 3. So when it's high, the output could be producing as low as 2.4 volts on a 5 volts device. Keep that in mind. We're not necessarily going to be able to put 5 volts out, even though it's a 5 volt device. It can only put out, but it's guaranteed to put out at least 2.4 volts. But usually, if you looked, it's about 3.5 volts. Now, the voltage when the output is low is going to be 0.4 volts maximum. And typically, it's going to produce about 0.2 volts. What that says is, from the perspective of the chip, when it's outputting a 1, it'll be a value from 2.4 to 5 volts, or whatever your power supply voltage is. If it's producing a 0, it'll be from 0.4 volts down to 0. If it produces a value between 0.4 volts and 2.4 volts, in that range, it has an unknown value. So we have to make sure we always drive it low or drive it high or let it be high. Any question about that before we move ahead? Okay, let's now talk about the voltage on an input. The voltage on an input, when it's high, minimum of 2.0 volts. The voltage on an input when it's low is a 0.8 volt maximum. And what I want you to notice is that our output satisfies this. Our output satisfies that. So we can plug safely our outputs into our inputs, and they'll always be recognized as either a 0 or a 1. That's a critical fact. Okay, let's talk about inputs or current for a second here. Currents. We're going to have a current on the output when we're high, current on the output when it's low, current on an input when it's high, and a current on an input when it's low. So the current when an input is high, it is minus 0.4 volts, which is minus 400. Wait a minute, am I reading no, I'm reading the right thing. Microamps. It's a max. Now, what the minus sign means is the direction the current is going. The current is going, when it has a minus sign, into the chip. So we'll leave that and we'll sort out all our minus signs when we're done here. When it's low, it's able to produce 16 milliamps. I think I have that backwards right now. I'll sort out the minuses when we're a little further along here, because I have it on my sheet here in a different order. So it can take 16 milliamps maximum. And actually, this is a sink. Instead of minuses and pluses, we'll use this. This is a source for now. That's just a reminder to me. So what this says is when the output is low, voltage is low in the output, this can provide 16 milliamps of current. Do you notice that's not enough to drive our LED? Now, we could get an LED that was high enough for, but in general, that's not good enough. Okay, let's look at the inputs. 40 microamps. What did I write up here? This actually is amps. Confusing myself here. This, of course, is a maximum. And then we have, when our input is low, we have 1.6 milliamps. I'll call that a maximum again. Okay. Now, we'll have to look at the schematic for you to understand the direction. I'm going to leave that off because that'll just confuse you for now. But notice that what we need for our input is 1/10 of what we can produce on an output. So, for example, our chip is going to be able to sink 16 milliamps of current from 10 devices, each producing 1.6 milliamps. That difference of 10 is not accidental. That says how many inputs can you hook to a particular output, and we call that the fan out. And on this device, the fan out is equal to 10. The other fact to know and tell here is that, remember up here we had on our input only need to see 2.0, but we're going to get as much as 4 or 2.4. This guy never gets any lower than that, which means they overlap each other, and so does the low values by 0.4. Here is something called the noise margin. And it's the difference between what the outputs will actually produce and what the input is expecting. In case we have noise on our line, it can be off by almost 0.5 volt, and we'll still recognize our high and low signals correctly. Okay, get rid of the words max here just because it's easier to read them, and they're all maxes. Now, there's 2 other numbers we would need to know about. Just one is called TP LH, and the other is TP HL. Remember, we're working with combinational logic. But one of the things I did tell you about the combinational logic is that things don't really happen instantly. There is something called the propagation delay. And this is the time. The T stands for time. The P stands for propagation delay. And this is going to be the delay that the signal needs to have to go from low to high or from high to low from the moment the inputs change. So the output will be ready based on some time. The maximum time for low to high is 22 nanoseconds. That's the max. Typically, it's 11 nanoseconds. To go the other way, it's 15 nanoseconds as a max, and 7 nanoseconds is typical. So for a particular device, if you measured it and it was really closer to 11 or 7, you could design for that. But you're right at the edge of what this can do if you're worried about these numbers. But for simulation purposes, you would need to know that the output's not going to change, perhaps for 22 nanoseconds. And since these are different values, you may get some intermediate answers as you're changing some bits on and some bits off, telling us that although combinational logic on paper happens instantly, in the real world, we may have to put some delays as to when we look at signals in order to be able to, properly, know they've changed and they're stable. So this would be some numbers I'd want to have somewhere. Now the data sheet for this, I found one finally that actually shows the chips inside. So the function table is an inverter. I'm actually not an inverter, a NAND gate. This is the truth table for a NAND gate as we've been using it. Here are where inside the chip you'll find the various gates. Now, normally, when you put a chip in the circuit board, you think about it as being this end is the top, this end is the bottom. But no matter how you think about it, we have to know where pin 1 is. Pin 1 on this design is, if you're in the vertical orientation, it's at the top left. If you're in the horizontal, it's at the bottom left. We count down the long side, 1, 2, 3, 4, 5, 6, 7, and then back up the other side, 8, 9, 10, 11, 12, 13, 14. Logic chips are typically 14 pins with VCC on the top right pin, or the top left, depending on how you're looking at the chip, and ground being opposite diagonally. This battery position here and this ground position here are shared by all of the internal gates. Although we don't see all the wiring here, we will. So if I needed to use these as A, one of these is B, and its output is here. We obviously could take its output and hook it to another input. We could tie two inputs together if we were going to build an inverter. So this is real world what you would get if you spent your dollar. This is what they'd send you. Anybody have any questions about the specs we talked about or about the diagram of the chip here? Now, I will tell you, I am going to come back to the source and sink thing. I erased it then because I realized I didn't have the picture of the transistor to show you that you need to see. We will get back to that. Any questions about this? Now, if we were all meeting together at the end of class tonight, before class was over, we would put some of these together and light up an LED using them. Unfortunately, we can't because of COVID, but maybe sometime you can come back and visit me and get to do it with the class. Now, inside this data sheet, the numbers we were just talking about. VCC, 5 is nominal, 475 to 525. High level and low level voltages, high level, low level currents. Notice we put a minus sign on the 0.4. On the outbound side, we put the minus sign on the this guy, the 1.6 milliamps for the input low. And those are still 10 apart. This is 16 milliamps. This is minus 1.6. So you could come to this table and get that sort of information. Here's the timing. It's the switching data. I got it from a different data sheet, but this has the same numbers it looks like. Here's what the chips actually look like. Well, we need a dip chip here. If you look down on top of it, there's a little notch and there's a little indent in the chip off to one side. That's where pin 1 is. Remember, you count down one side and up the other side. We saw that pins 1 and 2 are inputs to a NAND gate. The output was on pin 3. So we have to go refer to the other picture to see what's inside. There's a little ding here, which is part of its injection molding thing that might or might not appear on the chip, but don't confuse it with the actual thing here. But if we had these, we could plug them into a breadboard, wire them up, and all would be well. Here's looking at the end of it. You can see the pins. There's 14 pins that have to be plugged in. We need to plug VCC to pin 14, ground to the opposite diagonal. Then we have 4 working pins. Now, one of the things about TTL that's a little strange, inputs are always 1 unless you pull them low. So there's 3 things I could do to an input, right? I could pull it low, in which case it's a 0, and pulling it low means getting it less than 0.8 volts. I also could pull it high, get it higher than 2.8 volts or 2.4, whatever the number was. I also cannot hook it to anything. And if I don't hook an input to anything, it assumes a high value. It assumes a 1. Keep that in mind because you might not expect that. That means that if I leave pins 1 and 2 not connected, pin 3 will do what? Well, we have to look at the truth table. If both of these are 1, what's pin 3 do? Pin 3 low for us if we left the inputs high. Not a good practice, but it can be done. So if somebody asks you about the binary on this has more than 2 inputs, it does. It's got a 1, it's got a 0, and it has a not hooked up. And I don't think there's anything else interesting in here. There's some measurements. Well, this doesn't even have all the packaging. Yeah, here they are. Packaging measurements, so you know how to build your circuit board. Here's also a different area. Now, if you looked at this chip and you thought about it, there's a lot of transistors inside here. This one, not as much as some types, but because it's a fairly simple circuit. But how much of the chip do you think is taken up by all those transistors? 90% or 95%? Anybody take a guess at it? Samir, what do you think?
I'm going to say 90.
Okay. Robert, what do you think?
I'm going to say a lot less, like 50%, because it needs circuit board, it needs wiring. There's a lot more than just the transistors.
Okay, well, if you take all the transistors and the wiring that's inside this chip, it actually fits right in the middle of the chip in a circle about the same size as that little circle over there. Everything else inside here is empty, except there are little gold wires that go from that circle thing in the center out to each of the pins. The most likely thing to damage a chip is either you heat it up so much that the gold wire comes unsoldered internally, or you drop the chip and the little gold wire breaks. But the thing itself, certainly no more than the size of that circle, right in the middle of the chip. The rest of it is just simply plastic, and it has to be this size in order to stretch out the pins that far apart. They're, I believe it's 0.1 hundredth of an inch. I think it's 1/10 of an inch apart. And we should see that mark here. It is down there. Yeah, 1/10 of an inch. Okay, so let's explore this chip a little bit. Let's basically open up an inverter. First of all, let's first of all, let's just think about how with a transistor we would build something like this. Again, we're not actual values of things like resistors. Matter of fact, the main pictures I'm going to give you, those resistor values may not even be correct because I've put together the pictures from multiple places and I've also removed some circuitry to make it less confusing. But here's the idea. We have plus 5 volts applied to the top of this signal line. We have the signal coming in applied over here. If you think about this, if we put an LED and a battery over here, this is the same as the circuit we've always been using. Put a battery over here, that's the one I said we're going to replace eventually. Well, if we have a beta in the transistor that's much, much greater than 10, then the current through a resistor that's 10 times bigger than that one will certainly, when multiplied by beta, be bigger than the current that's limited by that. And will certainly, when this is made high, put this transistor into saturation. We'd see 0.7 volts there. And what would we see on that side? Raise your hand if you know. Can't be only two people that know. What would you expect to find, Mohammed?
Is it less than 0.7?
Yeah, the less than 0.7. Typically, we saw back on the other sheets, although I don't think I showed you I showed you transistor data sheet last time. The type we're using, this typically will be near 0.2 volts. But it's all we have to say is it's less than or equal to 0.7 volts. At exactly 0.7, we may or may not be saturated, and we have to watch it doesn't change. But the way we design them is very similar to this, except they're extravagantly adding a lot more here than they need if the beta is only 10. But this is kind of what we have to think about, is the idea of being saturated or not saturated. And this picture does a good job of telling us all we need to know. Let's look now that we're experts on that, inside of an inverter. That's the 7404 chip. Okay. Now enjoy that for a couple minutes. Give me a smiley face showing me how much you're enjoying looking at that. Yeah, I knew you guys love this sort of stuff. Now, what I want you to do is a couple minutes and think about what are each of the transistors going to be doing if we apply 0 or ground to the input. This is the input here. This is the output here. If I put a 0 here, we know a 1 is going to come out, or 5 volts, something close to 5 volts. What are all the transistors going to be? Which ones will be turned on? Which ones will be turned off? And then look and tell me, if it were a 1 or disconnected, we know this is going to be a 0. What would the transistors be doing then? We know they're going to be opposite what they would have been when it was on, but let's get some justification for why they are what they are. And remember, the values of the transistors aren't really important. The fact they're there is, but their actual values aren't. This diode here is a standard silicon diode, meaning it's forward biased and current does not flow through it if it's reverse biased. So let's take about 5 minutes and you kind of work by yourself there and see if you can figure anything out. Now, if you're talking to somebody else on Discord or something like that, don't talk to them for a few minutes. See if you can work it out on your own. I'll give you about 5 minutes. I'm going to even turn my microphone off. Okay. You should have at least got through a couple transistors here and have them ready to go. Let's start by putting ground on this pin right here, a 0. Who wants to tell me about Q1? I only see 2 people with hands up. You have to participate. Okay, Mohammed, tell me about Q1.
Professor, I don't know if you're supposed to give a value, but I think it will be in saturation
Why would it be in saturation?
because the current flow is lower than 0.7. I mean, it's just I think we talked about this in previous lectures, and it's just part of me says it will be in saturation because it's low.
Okay, that's close to the right. That's close to what I want to hear.
Okay.
If we lower the base, then we should be able to look out the base and see some power. Which, if we look through that resistor, which is a limiting resistor, we do see 5 volts. Because of that, that means there can be current flowing through here. If current flows through there, and these transistors and resistor values are designed to be either saturated or cut off, we would expect this guy to be saturated, just as he said. If that's the case, that means that the value across this transistor has practically dropped to 0 volts. So current hits the transistor, forcing the voltage across the transistor to be roughly 0 volts. Who wants to tell me about Q2? Scott, what would you say about Q2?
Well, the first thing I'm looking at is the collector to emitter path. Looks like we've got 5 volts on the collector side and potentially 0 volts on the emitter side, because that ultimately connects to ground there. So whether that flows through, I guess, depends on whether it's saturated. And
Okay. So we know this transistor is going to be, when we're ready here, saturated or cut off. It's going to be one of the two. If you're sitting on the base and you look that way, are you going to see a voltage that's high enough to turn you on?
oh,
Well,
no,
no, because the base is 0.7 above that, right? So that means this guy can't possibly be turned on because there's no way he can get current. So if there's no current flowing through here down, that means the voltage across him is going to be basically off, right? So he's off. And the other thing we could think of is that since VCE is a 0 here, that means there's 0 volts here. And this, if anything, is a little bit higher than ground. If we were able to get here, this would be a little higher than ground, which means it would be reverse biasing this, definitely cutting it off. So in this case, this transistor is off. Now, because it's off, we should know something about Q4. Who wants, Scott, why don't you tell me about Q4? Keep you going here, you're on a roll.
All right, so Q4 will be off because we can't
Why?
have any, we cannot have any voltage dropped across the base to emitter here.
Right, we know here that this is not 0.7 volt difference. Okay. We know that, as a matter of fact, it's slightly reverse biased if this resistor were doing anything, but at best it's 0. So if we have 0 volts here, and we have 0 volts here, there's no way we can get 0.7 there, is there? That's going to be 0 volts. Therefore, this transistor has to be off. Who wants to tell me about Q3? We'll let you rest a second, Scott. Get some hands up. You know plenty to do this problem. Yeah, some of you are like looking at this and going, uh-oh, there's more than one transistor. I don't know what to do. Your problems you've been working are harder than the ones we're working right now. And unless you've been slacking, you've already done these. Let's have somebody besides Robert. Robert talks too much. He's already been up too many times. So has Mohammed. Well, Mohammed, why don't you tell me about this transistor?
Professor, I think it will be turned on
Why?
because okay, so it's okay, so it is the Q3, right? If
Yeah.
we look at the 5 voltage, there will be minimum drop. It's not going to be as high as we were expecting it to be, but it will be smaller value, but it will be turned on, I'm pretty sure.
Well, I would take a different approach to it. What you're saying is going to work, but sit here at the base. We know we can't go this way, right? This transistor's off. There's a cut path there. We can't go
Yes.
down. If I follow backwards, will I ever get to voltage?
You should.
Oh, look at that. I got 5 volts.
Yes, you should.
Because I got 5 volts, that means current can flow. If current can flow, as long as I can get enough, this is going to be 0.7 volts. If this is 0.7 volts, this guy saturates and he's on, meaning that the voltage across him minus the voltage of 0.7 volts here, because we have another drop here, wherever we're headed, is going to put a value in here, roughly in that 3 volt range we were talking about that the voltage wants to be. It doesn't really make 5 volts. Well, if you get anything above 2 point whatever it was, 2.4 volts, it's going to appear to be a 1. So 0 in, 1 out. So we just saw this work like an inverter when we put a 0 there. And we'll go through that again, obviously, or you'll go through that again, because I want you to make sure you understand what's going on. Don't just copy this picture and be able to redraw it, because if I move any of the transistors around or give you a different circuit, you'll be completely lost. Do the thinking that these people that have been answering the questions have been doing. Way back up to 5 volts here. When this turns on, we know there's virtually no voltage drop across it. This is a small resistor So there's going to be virtually no voltage drop across it. We do know there's going to be a 0.7 volt drop across the diode. So that's going to take it from 5 down a little bit. Part of the reason we had to have a diode here, anybody want, that'd be a great test question, is why is there a diode at the output? Who wants to answer that other than Scott and Robert and Mohammed? Scott?
I'm going to guess it's sort of like a safety mechanism in case a higher voltage is introduced at VO here.
Okay, I like that for now. We'll learn a little bit more about it, but it's a one-way valve, meaning current will flow out of the top of the circuit only when it's high. So only when it's turned on and we're trying to produce a 1 will current flow down and out. Just a little sneak preview, when it's ground, it's going to actually flow in and down. And if it could flow in and down, it could also go up and out, and that wouldn't be good. So this is exactly like you say, it's a safety mechanism so that the current can only flow that direction. And we'll internally make sure it only needs to flow that direction when we're trying to produce a high output. We'll come back to that. Let me bring that same picture up again, and we'll take another case and take a look at it. Okay, let's assume, is that a red? No, I want to make these red. Oh, I can't, and this is paint. Never mind. So we're going to put a 1 here, or 5 volts, or leave it unhooked. Explain how we're going to get a 0 here. Let me give you like 2 minutes again to think by yourself, but use the type of thinking we were using on the last circuit. Think how cool you're going to be the next time you go to a party. You know, yeah, I can analyze that 7400 chip for you. Makes me kind of popular, doesn't it? I'd just be wonderful. You'll have to send me pictures of that. Just take a couple minutes. I'm not gonna. We don't have that much more left tonight. I want to get through this circuit before I give you a couple of homework assignments. Okay, I think that's enough time. You worked your way through that first transistor, and that's the only hard transistor on the entire page is the first one. This guy here. Who wants to tell me about him? I'm starting to see a trend here. Okay, Samir, tell me about this.
I would think it would be saturated.
This guy?
Yeah.
Hey, tell me why.
Because of the 5 volts on the top right.
Okay, but we have 5 volts here also.
Oh yeah. Oh, that also has, yeah.
Okay. So if we have 5 volts on the two sides, the base and the emitter, Robert, tell me about that. Is that going to turn it on or off?
I think it's going to be cut off because the 5 volts does have some resistance there.
Right. And this also probably not really completely 5 volts, because remember we said that it might only be as high as 3 something.
Right.
But there's not enough to get 0.7 volts there, which means this transistor is off. If it's off, means it's the same as there's an infinite difference between these two. This 5 isn't jumping over here or something. So how about Q2? Patricia?
I think it will also be off since you're not getting any current from the base.
Okay, now this is actually a tricky issue right here. We know from the last picture we drew, it was off to be on here. How? Mohammed, you want to tell me how?
Professor, I was actually thinking a different approach. Like there's 5 watts, and if we go through 1.6 inverter, it will definitely reach Q2, and we'll have enough current to flow through.
Well, no, this can't have any. This will have no effect on whether this is on or not. Only the base emitter does.
Okay. All right. Then why not?
Okay. Well, here's the deal. If I stand here and I look backwards, can I get to that 5 volts? A while ago, I couldn't because we had pulled this to 0, which meant the transistor had roughly 0 volts there. But if I look backwards, this is the collector. That's the base. The collector is an N. This is a P. That's a diode. I can see right through that diode, through the resistor, up to the 5 volts. Meaning this transistor is definitely turned on, and this is pulled down to roughly 0 volts. If this is grounded, what's going to happen to this transistor right here? It's not quite grounded because we got this 1K resistor in here. But Frank, what do you think?
Well, I'm guessing because it's grounded, Q3 would be off.
Well, we have ground here. Now, let's think about that a second. It's not exactly grounded. If you look at this transistor right here, which we know has to be on, we know that has to be on, and we know this one has to be off, but let's justify it. Because that's the opposite it was in the last picture. In order for this to be on, this has to be 0.7 volts right here. Right, because we need to have base emitter of 0.7 volts. So this guy is still about 0.7 volts by the time we get here. However, this 0.7 volts we have a transistor here with a resistor that's got to have enough so that the point right here is 0.7, and this is 0.7 higher, or 1.4 volts. Well, the reason here is we had 0.7 to get to here, and we've got a saturated transistor that could be as high as 7 volts, giving us the 1.4, which does turn this on. 0.7 here, 0.7 there, meaning now that this is off. This guy was on. So in order for this to be on, this value has to be 1.4, because we had 0.7 across this, 0.7 across the base. We know when this turns on, this is going to get pulled to 0.7, and this is more than likely about 0.2, whatever. This is no higher than 0.9 volts, maybe. Well, 0.9 is not as big as 1.4, so that transistor has to be off. And because it's 0.7 here, this one's on. Now, the current that's out here, when it's off, flows into and through the transistor to ground. So rather than coming out, it flows in. This is even though stuff is going into the circuit. This is the output. When it's a 1, it goes out. When it's coming in, it goes the other direction. This can tolerate 16 milliamps coming in. And when it's going the other way, it can only provide 400 microamps. When this is a 0, this has to come out of the input. And it can come out as much as 1.6 milliamps. Because 10 of them could go into a chip somewhere that has to absorb 16 milliamps. Also, this has to be able to take in 40 microamps. Which is, if this is providing 400 microamps to a device that, you know, these are outputs, it's going to its inputs, and we can do 10 of them, they have to be able to sink 40 of the microamps. So we've done a fairly good analysis of this inverter. Part of the reason we talked about resistors first and then diodes and then transistors was to get through this circuit when we got to it. So obviously, the next step is this. This is a NOR gate going on. Not a lot when you look at it carefully. The other thing is this guy. This is a NAND gate. Look at this funny looking transistor here. This transistor has 2 emitters. Either one or both taken to ground will turn that transistor on. If they're both high, it'll stay off. So your homework assignment is to go through those 2 new circuits I showed you, the NAND and the NOR. And for both the case when they're 0 and the case when they're 1, tell me what the state of all the transistors are. It won't take you long to do if you paid attention tonight. So in this case, we have 4 cases we have to handle. You have A and B and Y. You have 0, 0, 0, 1, 1, 0, and 1, 1. The outputs in these, because this is a NAND gate, should be 1, 1, 1, 0. For each of these cases, all 4 cases, you need to tell me what each transistor. You just have a little piece of paper that says Q1 is on, Q2 is off, D1, well, Q3 is on or off, Q4. Just list for me for each of these cases what all those transistors are doing. Then do the same thing for a NOR gate. For all 4 combinations that A and B can be, tell me what the transistor, I believe this has 2 more transistors than the other one did. It has transistors 5 and 6. That shouldn't be that challenging to you. Now let's download this. This is on the website. Let me see what I named it. think it's /ttl.zip where TTL is all uppercase. I don't have it written down anywhere. Let me do it again. So there's the thing, and it has 4 files inside, or 4, yeah, I guess files inside of it, 2 of which are your homework assignment. And think it through carefully. Don't try to look it up online or to do something. Use your brain. Don't use your partner's brain, your friend's brain, your mom's brain, your dog's brain. Even though it makes sense yours, use yours. We're trying to develop yours. Try to work through the problem. If you get stuck, you can talk to other people, but not about the answers. You don't have somebody else do the problem and think you, oh yeah, I did it. I wrote down all the answers. That's not doing the problem. And there's motivation for doing this. There's reasons why you need to be able to do these that are going to be in your future soon. Anybody have any questions? Who is that? Somebody, Michael?
It's Mikel. And which ones were supposed to do? NAND and not?
NAND and NOR.
NAND and NOR. Yeah.
NAND and NOR. We did not, well, NOT is the little transistor example. Anybody else have any questions about that? Learning those rules of saturation and about diodes and things like that come in very handy when you're working on a problem like that. Let's get the syllabus here and see where we are. We got a couple minutes we need to burn up here. Where is my syllabus for this class? This is 231, right? Oh, is it? Okay, so we did tonight. We have a couple things to do here. This introduces us to some of the necessary things we're going to need to do to flip over to sequential logic on the next session. So once we get to sequential and flip-flops and things like that, then we'll start worrying about propagation delay, setup times, hold times, all of those types of things. My guess is that one of those 2 nights, probably this night, we'll have some sort of in-class exercise. It won't be a quiz, it won't be a test, but it'll be some sort of an exercise worthy of a grade. Might be that I just go down the roster and I ask each of you a question. Could do that. Twice ask each 2 questions. In any event, you kind of expect that there might be an activity during Unit 8 somewhere, because quite honestly, we can cover the capacitor thing fairly quickly. Well, maybe not. Depends on which part I'm going to. Sometimes I do an extra unit with that, or it's a subunit of that. And 555 timers are just another integrated circuit we have to analyze. Yeah, you might want to think about studying up really good on these transistor problems and some of the other material we've been covering. It's highly unlikely I would ask you to do a Quinn-McCluskey with 8 inputs, in a oral, questioning session, but could be. Probably not that many inputs. So. Okay, 5, 4, 3, 2, 1, I think coming up here, and you all can tell me good night, and I will see you next Monday night, I guess it is.
Good night, Professor.
Good night.
Good night.
Good night.